Hello YouTube, today we're doing a problem on Newton's laws. This is a very typical Newton law kind of program involving ramps. So you got Jack as a person holding onto a 200 kilogram box that's sliding down a ramp, angled at 45 degrees above the ground, and you're given the coefficients of static and kinetic friction respectively. So you have this scenario here. Jack is pushing a box down this ramp here at a certain degree theta, which is 45 degrees, and the box weighs 200 kilograms. Excuse me, it has a mass of 200 kilograms. So, however we want to define our coordinate system to make life easy, you're going to angle it so that the x-plane, or the x-axis, excuse me, is the hypotenuse, and then the y-axis will be perpendicular to that. So you'll do that. Why? Because the calculations will be easier when you're approaching a Newton's law problem such as this. So first thing you always want to do when approaching a physics problem involving Newton's laws is to draw a free body diagram. So let's do that. Each point there represents each object, so that dot on the right represents the person, that dot on the left represents the box, and we're pretending that all of its mass is situated at one point. So let's start with the box. So we have the normal force, and that's the force pushing back perpendicular to the surface, so it's at that angle there. We also have the gravity, which is straight down, and we also have the force of Jack pushing, and as we know, with every force there's an equal and opposite force. So like the force, if you push in one direction, that means the box is pushing back, or vice versa. There's an opposite force, so that's the force of Jack. And then, excuse me, he's holding onto the ramp. So, anyway, so then we have the kinetic friction, so as well, making sure that the box is in place. So, then we got the normal force for Jack, and gravity is acting on as well, but we also have the force of the box acting on Jack, and also the coefficient of friction, or the friction acting on Jack as well. So we're going to use this free body diagram to approach the problem here, which is given here. If the box slides down the ramp at a constant speed, how much force is Jack pulling on the box with? Okay, so constant speed meaning the sum of the forces are equal to 0. And how much force? Well, is we're going to call that the force of J, meaning Jack. So, given information, we got the mass of the box, we got our kinetic friction because it's moving, right? It's not static anymore. So that 0.5 there is there to throw you off in case you use the wrong coefficient. We also have gravity, which is 9.8 meters per second squared. And to set up the problem, if they're going at constant speed, when we set up a Newton's problem, we're going to look at the vertical and horizontal components of the forces acting in the system. So for the horizontal components, we're going to look at the horizontal directions, in this case the 45-degree angle slightly upward or downward in the free body diagram. So that's the force of Jack, the force of the friction, and the force of the box. So we know that the force of friction, which you can see here, minus or plus the force of Jack, which is on the left over here. So looking at the box diagram, look at the right side of the dot there of the free body diagram, is going to be opposing the force of gravity that also has an x component to it. If you take a look, you can look at this, since we defined our coordinate system, we have a vertical component and a horizontal component to gravity. Here, this is a vector. Same thing here, we got a vertical component and a horizontal component. So this is the force of gravity in the x direction. I'm just going to put x and y. So this is the x direction, this is the y direction, and this is the x direction, this is the y direction. Now why are we subtracting it? Well, we denoted this direction to be positive and this direction to be negative. So that's kind of why we do that there, because the sign shows direction. So that's why we subtract that force of gravity there. So we added these two and subtracted the x component of gravity. Then simply plug in the information that's given, like what do those forces represent numerically. Well, we know the force of friction is mu times the normal force, and we're looking for the force on Jack, so we're just going to leave it like that. But what's the force of gravity in the x direction? Well, if you take a look at this here, using geometry, you will be able to determine that this angle here is also theta. It's kind of weird to determine there, but I suggest drawing a triangle and seeing it out. But due to time purposes, I'm going to skip that explanation. I kind of want to go into it in detail, but definitely look that up to truly understand why. But we're just going over a setup here. But it would be mg sine theta once you look at all the trig portions of it. Now, since we're looking for the force that Jack is pulling on the box with, solve for this portion here, and you'll get that there as well. So, what about the y directions? So we're dealing with this stuff now, just the y components. So that means the normal force is going to cancel out the gravity, in other words. So the force of normal is just n, and then doing trig again, you'll get mg cosine theta for the force of gravity in the y direction here. In the y direction, yeah. And then you'll solve for normal here. Why? Well, because you can make life easier, because you can sub that into there's doing like two systems, two equations with two unknowns. You can solve for one and get the other kind of method. So combining that together, substituting n in for mg cosine theta, you get mg sine theta minus mu mg cosine theta. We'll show it over here to make it look nicer. So this is what we got by plugging in n. And then you can make life easier by taking out an mg, just factoring it out to make calculations much simpler, less writing. Then you plug in the numbers. Mass is 200 grams, remember. Gravity is 9.8 meters per second squared, and the angle that was given in the problem was 45 degrees. So even if you messed up the sine and cosine in this case, which is a very common mistake, you'll actually still get the same answer because the sine of 45 degrees and the cosine of 45 degrees are the same, radical 2 over 2. So you'll be okay, but make sure you do not mix up the sine and cosine when you're doing the problems in the future. And you'll get an answer of 832 newtons. That's how much Jack is pulling on the box. So that was a pretty good example problem. Hope it helped. I guarantee you, if you're taking a physics class, they will show an example like this. So hope this helped in terms of setup and a bit of explanation. All right, good luck, happy studying, and keep practicing.